Good evening. Welcome back to AP Stats Notes Online. I'm going to be switching over from talking about sample proportions to talking about sample means. I mentioned in the notes for 7-2 the sample proportion, the sampling distribution for sample proportions, that we know that sample proportions and sample means are both unbiased estimators. And so we like to discuss those. And very often, depending on what you're measuring or wanting to try to measure on a population, very often it's going to either be a proportion or a mean. And so it makes a lot of sense to talk about either one of these two statistics. Again, not the only two statistics out there, but certainly the ones that get discussed more often than any of the others. So we know some things about the sampling distribution of sample proportions. We know that the sampling distribution can be a normal distribution as long as that normal condition is met. We know that the center or the mean of a sampling distribution of sample proportions will be equal to the population proportion. Because it's an unbiased estimator, and we have that formula for the standard deviation, where we square root, or actually we multiply the success rate times the failure rate, divide by the sample size, and then square root that, and that gets us to our standard deviation. One thing that hopefully you're noticing as we go through this is that the standard deviation in a sampling distribution is smaller than the standard deviation of its population. And if we haven't notice that yet, that has a lot to do with the fact that the population distribution, when we're talking about proportions, very often is a bar graph that wouldn't have a mean or a standard deviation. So if you haven't sort of thought about that or realized that the sampling distribution will have a less variability, then you're going to find that out throughout the course of this discussion about sample means. So let's get to your notes. Based on the penny activity, and I'm going to go ahead and tell you now that we're not going to do the penny activity. So we can ignore that for now. And get to this applet activity. So this is based on the applet activity. What do we know about the shape, center, and spread of the sampling distribution of a sample mean? Now what applet, the notes are talking about, is this applet that comes from something that Rice University had put out. If you Google search Rice University sampling distributions, you'll get to this website and get you to the sampling distribution applet. And so what I'm going to show is a couple of things here. All right, if we're talking about mean, right, if we're talking about a population mean or a sample mean, then we're talking about a quantitative variable. It's very possible that the distribution of a quantitative variable could be normal or could take on any shape, skewed, uniform, bimodal, but although we don't generally get to see that, again, just bimodal would look something more like this, right, where there's two distinct clusters. I want to make sure that we're clear about that. There have been some confusions in the past. So I'm going to just take a look at a normal population distribution and then a skewed population distribution. And what I'm going to ask the applet to do is to pull samples of different sizes from a population, at least originally, where the distribution of these of this quantitative variable is normal, with a mean of 16 and a standard deviation of 5. Right? So if I ask it to pull a sample, so it's a bunch of numbers in here, it's going to pull 5 numbers, because that's the sample size I asked it to do, 5 numbers, calculate the mean of those 5 numbers, and drop that mean calculation into the sampling distribution here. So population distribution, this is all the individuals and the measures for those individuals. This is a sample of 5 of the individuals from the population. So this is your distribution of sample data. And then we're going to calculate the mean of these 5 and drop that mean value in as the first value in the sampling distribution. Now, to talk about the sampling distribution doesn't make a ton of sense so far because we only have one number in there. So I'm going to ask that the applet produce 1,000 more. So we have 1,001 samples represented in here. How would you describe the shape, center, and spread? Well, the shape, if we try to fit a normal curve to it, looks to be approximately normal. Again, approximately normal. It's not perfect. Nothing's perfect. So this is going to be approximately normal. And look at the mean. The mean is 16.05, just as, and it's really, really close to the mean of the population. Again, sample means is an unbiased estimator, so that shouldn't be very shocking. Look at the standard deviation. Standard deviation in our sampling distribution is 2.29, whereas it's 5 up here. So the variability has gotten less. Again, hopefully conceptually that makes sense, because in a sampling distribution we're representing a lot more data, because every number inside of that sampling distribution represents a sample of 5 numbers. So it represents more data by a factor of 5, and so anytime we get more information, we should be we should be more accurate in our calculations, and so therefore less variability. So the standard deviation does go down. We'll talk about how it goes down in just a second. Now we can increase this to 2001, 3, 4, 5, go all the way up to, well, I don't know what happened there. But anyway, I think I cut off some of the animation. But go up to 10,594 reps. And what we're finding is that the mean is still pretty close. The standard deviation is still smaller than the original. Okay, so let's clear this out. I'm going to do this again to make 10,000. Okay, something happened in the numbers there. So anyway, I've got 10,000 samples pulled from the exact same population, and the mean is about 16. Standard deviation is back to where it was when we pulled the first 1,000. So anyway, if we were to describe this sampling distribution, if we do it again, it's approximately normal with a mean of pretty close to 16, the standard deviation that's smaller than the original. Okay. Now, what if we did this from a skewed distribution? Very skewed right? And so I'm going to ask it to pull 5 numbers, drop it down, calculate the mean, and drop that mean down into the sampling distribution. And I'm going to do that another 1,000 times. Okay? Now, take a look at the sampling distribution as it sits. If the sample size is 5, then it's a lot less normal than our sampling distribution was when the population distribution was approximately normal. As a matter of fact, the sampling distribution seems to mirror the population distribution a little bit. So this is very heavily skewed right. The sampling distribution is not as heavily skewed right, but you could definitely make an argument for it being skewed right. A lot less normal than the previous example. So we didn't point this out before, but with this skewed right distribution, the mean was 8.08, standard deviation is 6.22. So if you look at the sampling distribution now with 1,001 samples, the mean is again pretty close to 8.08, 7.95, and the standard deviation has dropped. Okay, which again conceptually should make a lot of sense, but not quite as close to normal. So what we're starting to see here is that the sampling distribution shape tends to want to take on the same shape as the population. And that becomes a bit of an issue for us because we like normal or approximately normal distributions. It makes probability calculations a lot easier. But Anyway, we will account for that little issue in the next set of notes in the series. For now, I just wanted to show you that the sampling distribution tends to mirror the population distribution, at least for small sample sizes, and that gives you some foreshadowing into the next series. Okay? Now, what do we know about mean standard deviation? And again, there isn't a whole lot of reveal as far as that goes. So let's go to answering some of your questions in your notes. Based on the applet activity, and again, we'll pick that up here. What do we know about the shape, center, and spread? Well, the shape tends to be the same as the shape of the population distribution. And just because I know what's coming up next, I'm going to include for smaller sample sizes. Okay? The center of our sampling distribution is going to be the same as the mean of the population, or close to. I guess we really shouldn't say same. We should actually say close to. And then the spread of the sampling distribution is going to be smaller than the spread of the population distribution. Of the population, you can just say the population, but I'll say population distribution. So, shape, again, depends on the population distribution. The mean of your sampling distribution of a sample mean, and again, notation, mu sub x bar. So this lets you know that we're talking about the mean of a sampling distribution of means, when in the previous set of notes we were talking about mu sub p hat, which lets you know we're talking about the mean of a sampling distribution of a sample proportion. Well, this is just going to be equal to the population mean mu. Standard deviation of x bar, which would be sigma sub x bar, okay, is going to be smaller than the population standard deviation. As a matter of fact, how much smaller? Well, what we do is we take the standard deviation and we divide it by the square root of the sample size. And again, without a whole lot of reveal of where that comes from, if we can just accept that and move forward, because we do know it's going to be smaller, and it's going to be smaller by a factor of the square root of the sample size. Okay? Now, notice this note here, and this is in your book on page 444. There'll be a little white box in the margin that says AP exam tip. Use notation correctly or not at all. Okay? Make sure you understand the difference in the notations. P, p hat, mu, x bar, sigma, s sub x. What mu sub x bar is, what sigma sub x bar is. The difference between capital X and x bar. And we're going to talk about that in the example that we're going to come to in just a second. If you don't know if you're confused with the notation, then don't use it at all and use your words. Write out in words what it is that you're calculating, what you're talking about. Okay? Anyway, this is what we've got going on. Let's see about using it. Okay? So describe the same. So I mentioned before, the sampling distribution shape depends on the shape of the population distribution. And we see that in the next question, describe the sampling distribution of a sample mean when the sample is taken from a normally distributed population. Well, if it's from a normally distributed population, then the shape is going to be, again, approximately normal. We don't want to say normal. It's a big deal there, okay? The center, again, is going to be the same, or actually close to mu, the population mean, and the spread is going to be smaller than sigma, or the population standard deviation. Okay? Does the sample size matter? Well, as far as shape goes, no. For shape, no. Actually, for shape and center, it doesn't matter. Where it matters is the spread, right? For the spread, the sample size does matter. And that's because of that calculation. Again, as a quick reminder, we're dividing by the square of the sample size. So if the sample size changes, then what the spread ends up being for the sampling distribution is going to change as well. So anyway, let's start to use this a little bit. At the Nutty Peanut Company, dry roasted shell peanuts are placed in jars by a machine. The distribution of weights in the jars is approximately normal, with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. Without doing any calculations, explain which outcome is more likely. Is it more likely to randomly select a single jar and find the contents that weigh less than 16 ounces, or is it more likely to take a random selection of 10 jars and finding that the average content weight is less than 16 ounces? And without doing calculations, and as I'm reading through that, you're thinking a little bit. Hopefully you are thinking now that it's more likely for a single jar I'm just going to say to weigh less than 16 ounces. Okay? If we're pulling from a population whose average weight is 16.1 ounces and standard deviation is 0.15, then again, if we're taking, the more information we get, the less variability that we have. So we get more information from randomly selecting 10 jars and calculating the mean than we do from just choosing one and finding the weight of that one. So since there's more information coming in the sample, then it's going to have less variability in its distribution, and therefore less sort of varying from the mean of 16.1, and so it's going to be more likely for one jar to weigh less than 16 ounces. Okay? Now, we can test that theory by actually finding the probability of each event. Okay? Now, here's what I'm going to do. X, I'm going to let capital X stand for the weight of one jar, and X bar be the average weight of 10 jars. Okay? This is coming straight from, the weight of one jar is coming straight from the population. The population is approximately normal with a mean of 16.1. And the standard deviation of 0.15. Okay? So that means this would be 16.25. This would be 15.95. And we could keep going. Okay? But I'm going to stop there. So I want to find the probability that one jar, capital X being one jar, is less than 16 ounces. Well, that would put me about right here. Less than 16 ounces means that we should anticipate this probability being just a tick less than 50%. And so two ways to do this. Remember, we're in a normal calculation situation here where we can do a z-score, do 16 minus 16.1 divided by 0.15, get into table A, and we can pull straight from table A, since table A always gives us probability less than. Or we can get normal CDF, which is what I'm going to do. So second, VARS, normal CDF, the lower bound being something really, really small to get us out in that tail. I typed in a negative 1,000. The upper bound being where we want to stop our interval, which is going to be about right here, so 16. And then we need the mean and standard deviation. The mean is 16.1, standard deviation is 0.15. We type that in, and we get actually, this says 0.25. Oh, okay, which actually makes sense. If you look at where I shaded this curve, 16 would actually be closer to the 15.95, so it would actually probably start about right here. I don't need this part, so that actually might make a bit more sense. So 16 is going to be about right here, okay? Now, compare that to taking a sample of 10 jars. Well, the sample of 10 jars, we know that this, now we're getting into pulling an average weight of 10 jars out of a sampling distribution, where the shape is going to be approximately normal as well, because it's coming from a normal population distribution. So we're in the situation of a normal curve, and that's pretty terrible. Whose mean is 16.1. And so it's going to be approximately normal with a mean of 16.1. And then a standard deviation of something a little bit different. So we got to take 0.15 divided by the square root of 10. Okay? And this is going to be the mean of our sampling distribution. So 0.15 divided by the square root of 10. And the standard deviation of our sampling distribution is going to be 0.047. Okay? So 0.047, which means I'm going to just do the standard deviation less things. I got to get to 16. If I subtract 0.047 from 16.1, I get 16.053. I'm not even to 16 yet after one standard deviation, which I already was over here. So you can imagine that this normal curve is a little bit more narrow with less area out in the tail. As a matter of fact, I get the second standard deviation and it's 16.006. So I have to go all the way out to the third standard deviation to get to 15.95. Or 15.96. So 16 won't even get all the way, we'll have to come all the way out here. So our probability should be a lot smaller. So the probability that X bar is less than 16, again, you can get into table A and Z scores and help yourself if you'd like. I'm going to do second VARs, where the normal CDF, with a lower bound of, and I'm going to keep that negative 1,000. Upper bound is still at 16. My mean is at 16.1, and my standard deviation now changes to 0.047. I type that in, and the probability of me selecting 10 jars and the average weight of those 10 jars being less than 16 is actually now 0.017. Much, much smaller than just pulling one jar, and one jar weighing less than 16 ounces. Okay? So this makes a huge difference. We get into a sampling distribution, we have a lot less variability. So our average weights of 10 jars should be centered more around 16.1 than our population distribution is. Okay? All right. So at this point, I think we want to stop the notes, and the next thing we're going to want to talk about is the central limit theorem, which helps us out if the population distribution is non-normal. But we'll talk about that in tomorrow night's notes. We'll let this idea of a sampling distribution of means kind of sink in and some of the calculations there. Okay? Enjoy your night. Homework that goes with this is obviously in the text that was sent out. You'll have some time in class tomorrow to work on that, as well as we'll take care of any questions you have from section 7 to the sampling distribution of sample proportions. Okay? See you guys tomorrow.